Hi friends, hope you are all doing well. Welcome to Math Question Bank 12, and today I'm going to discuss four questions and then I'm going to solve them. So these questions essentially are coming from algebra, coming from geometry and trigonometry, and also coming from calculus and differential equations. So let's begin. I'm Dr. Ganguly. So the first question asks you to solve this equation here, that is x square minus x cube equal to 12. So looking at this equation, we know that this is a cubic, so it's going to have three solutions and we need to find that. Now to solve this equation, what I do is I take 12 to the left hand side, and now the big trick is there in this particular equation is that I have to factorize this equation somehow. And if I can see that 12 could be written as 4 plus 8, then I can easily write minus 12 as minus 4 minus 8. Now this immediately leads me to writing 4 as 2 square and 8 as 2 cube. And this step is important because this problem has been given in such a manner that this is amenable to factorization. So now what I can do, I can write x square minus 2 square as one term, and I can write minus x cube plus 2 cube as one term. Now I know x square minus 2 square can be easily written as x minus 2 into x plus 2, and the second formula is less well known, and that is a cube plus b cube is a plus b into a square minus ab plus b square. So this is a formula you should remember because it's often very useful in solving simple equations, specifically cubics. So if we use this equation, we can write x cube plus 2 cube as x plus 2 into x square minus 2x plus 4. Now, of course, we see that we have got x plus 2 on both these terms in this equation. And so in the next slide, I'm going to try to simplify this. So let us try to simplify this equation. So what I do is I rewrite the same equation here. Then I bring the x plus 2 to the left hand side, and inside the square brackets, I have the remaining term. Now, if I look carefully at the expression inside the square bracket, I can write this as negative x square. There is going to be a x term and a 2x term, so that's going to give me 3x. And then there is going to be minus 2 minus 4, that's going to give me minus 6. Now looking at this, I immediately know that one of the solutions is x is minus 2 because x plus 2 is going to be 0. So that's one of the roots which I have given in green. And the second root is going to come from solving this quadratic equation. So I can easily solve this. Remember, the formula for the quadratic is there. If you do not remember it, I have derived it in one of the previous lectures, and I immediately get the solution as x is 3 plus minus root negative 15 by 2. Now, of course, here you have a negative number, the square root of that. So since you know that I is root of minus 1, I can immediately write the second root as x is 3 plus minus I root 15 by 2. So this is actually the second and third root for the equation given here. Now let's come to the next problem, and this is question 2. And this problem, you have a triangle. The triangle is specified into two regions which are both right angle triangles, and the yellow triangle has the area given by 294 millimeter square, and you have to find the area of the blue triangle. Also, these angles are given as x and 2x. The length of this side here on the yellow triangle is 36 millimeter. All these dimensions are in millimeter. So we are going to try to write some equations here. That's obviously something we need to do to find the remaining sides of the triangle, which are going to help us figure out this particular area of the blue region. Now, first thing we do, of course, in such problem is we create some nomenclature. So we say the side of this blue triangle is A, the side of this yellow triangle is B, and the height here is h. And so I can immediately then write two equations, that is half BH is 294. That's the formula of the area of a right triangle. So remember, if it was a rectangle, it would be BH. So half of that would be half BH is 294. The second equation I get is from Pythagoras theorem that gives me b square plus h square is 35 square. So b square plus h square is 35 square. And now I have these two equations in pink which I could solve. Because I have two equations, I have two variables, I could solve them. So I can immediately write b in terms of h as b is 588 by h, and then I substitute it into the equation I obtained from Pythagoras theorem. So that's going to give me 588 by h square plus h square equal 1225. Now what I can do is I can multiply this equation throughout by h square. So that's going to give simplify it, and it's going to give me h4 minus 1225 h square plus this term here, which is actually 588 square. So interestingly, I have obtained this equation which is a quartic, but if you look closely you will clearly see that I can solve this for h square using the quadratic formula because it's a quadratic in terms of h square. So I plug all the values in the formula, and fortunately what happens is that the expression under the square root is actually a perfect square. So that comes out to 343 here. So I get the final result of h square having two possible values, 784 and 441. Now, interestingly, both these values are reasonable because they are both positive values, and so we are dealing with a geometric figure. So that's okay. We can now continue further and get h is 28 and 21. So we have two solutions here. Now, of course, I can immediately go back to my equation and write b is 488 by h, which is going to give me 21 and 8. So essentially, and very interestingly, I have obtained two solutions here, that HB is actually a pair. It could be 28, 21, or it could be 21 and 28. So now we need one more equation here because we have found B and H, but we still need to find A. And somehow we need to use the fact that X and 2X have been given here, and there is a relationship between these two angles here. So let's do that. Now what will come to my mind is that I could write an equation for tan x and I could write an equation for 2 tan x because a, h and b are there. So let's write tan x, that's going to be a by h, and tan 2x is going to be h by b. So remember always that tan of an angle is going to be the opposite side divided by the adjacent side. So that's what we have used here. Now I have tan x and tan 2x, but I may actually not need x. I really am interested in a. So what I do is I use the formula which links tan 2x to tan x, which is tan 2x is 2 tan x by 1 minus tan square x. And I can immediately substitute the values of tan x and tan 2x into this equation, and I can simplify this further. So essentially what I do is I again take this h squared term up here, one h term goes down here, so I get this equation. There is some cancellation of the h's here, so I get 2ah by h square minus a square. Now looking at this term here and the h by b term here, I can write the equation h square minus a square is 2ab. So there is a cancellation of this h and this h. Now from this equation I can write the quadratic a square plus 2ab minus h square is 0. So this formula in pink, this is our third key formula, and this actually relates a to b and h. And since I know b and h, I should be able to calculate a from this formula. So let's do that. But actually we have to do this twice because there are two possible combinations of h and b. Which first one is 28, 21. So we take the equation a square plus 2ab minus h square is 0, and we substitute here h is 28 and b is 21, and after some simplification I get this here, and then I can immediately solve this quadratic using the quadratic formula, and again it turns out that I get a perfect square here as 4900, so the root of that becomes 70. So now I have two solutions for a. Fortunately one of these is negative, so I can dump that solution and I can only go with the positive solution, which is 70 minus 42 by 2, and so that gives me 14 millimeters. So that's the solution. HBA is 28, 21, 14 millimeters. So that's one possible solution for this particular triangle. But we also need to look at the second solution we had obtained in terms of HB, which was 21 and 28. And so we again take our equation for A and we substitute here. B is 28 and H is 21. We simplify this here and it comes out as a quadratic. We use the quadratic formula. We get the expression here. Fortunately, 4900 is a perfect square. So I get here 70 as the square root of that. And again, I have one negative root which I can discard because this is a geometric figure. It won't have negative values and so on for the dimensions. And therefore, I get 70 minus 56 by 2, which gives me 7 millimeters. So that's the second answer, that HBA are a triple of 21, 28, 7 millimeter. But we are not asked to actually find the sides and dimensions of the triangle. We are asked to find the area of this blue region A. So that's going to be half AH. And so I can immediately plug in A as 7 and 21 in the first case where this combination was there, and I get A is 73.5 millimeter square. And again, I have the expression here, HBA is 28, 21, 14 millimeter. So I can take A is half AH is half 14 into 28. That gives me 196 millimeter square. So I have these two possibilities here in terms of A here. And of course, both of these are legitimate possibilities. So this interesting problem has two solutions, and using this problem, you can test the knowledge of the student in terms of certain basic geometry, certain algebraic skills, and also trigonometry. So it's not such an easy problem to do. Now, of course, there may be solutions out there by using geometry and so on. And if you know of such solutions, please give them in the comment section of this particular video. Let's now come to question number 3. And question number 3 asks you to solve a differential equation. Now, this kind of second order differential equation is very popular in many interview settings. And this differential equation also provides you with two initial conditions here, that is x0 is 1 and dx by dt0 is 2. So this is a very typical differential equation you get in many engineering, physics systems and so on, where you have to find some variable x which is a function of time. So let's try to do this. Now, of course, these kind of differential equations, you can easily find the solution by substituting that xt is e to the power st. And if you take the derivative, you take the second derivative and you substitute it, you get this equation here. Now, of course, you know that e to the power st is not going to be 0. So the term in bracket, this is 0. This is known as the characteristic equation. So I immediately find the value of s using again the quadratic formula, and that comes out to minus 2 plus minus root 3. So I can write the solution of this differential equation. This is actually the general solution as C1 e to the power minus 2 plus root 3t plus C2 e to the power minus 2 minus root 3t. So I've taken these two values of S, I substituted it here, and so I essentially get the solution as a linear combination of these two particular solutions. Now, of course, we are not finished with the problem because the initial conditions were provided. So what I need to do is now I need to substitute these initial conditions and get C1 and C2. So in this problem, we have the derivative, the second derivative here. That's why we need the two constants and we need two initial conditions to find them. So let's take xt, let's differentiate it and get dx by dt. And now let's plug in the value of 0 as far as time is concerned. So when we do that, we get x0 is c1 plus c2 is 1, because e to the power 0 is going to be 1 in both cases. In the second case also, we plug in t to be 0. So again, e to the power of t is going to be 1. So I'm going to end up with this equation here. The right hand side is provided as 1 and 2 for x0 and dx by dt0 respectively. I can now write this in a cleaner form by saying that C1 plus C2 is 1, and then this into C1 plus this into C2 is 2. So these two equations are simultaneous equations. You can easily solve them. Many students make a mistake in terms of solving this equation, so it's a good idea to let them solve them because that's a show of their meticulousness and diligence. So one easy way to solve these equations, which is take the equation which you had like C1 plus C2 is 1 and multiply it completely by the coefficient of C1 in the second equation. So that's what I've done here. I have taken C1 plus C2 is 1 and I have multiplied it by that coefficient minus 2 plus root 3 throughout. And if I do that, what happens if I subtract these two equations? The C1 term will cancel out and I will get minus 2 plus root 3 and negative of this expression. So that will become positive 2 positive root 3, and this is going to be the coefficient of C2. Now on the right hand side I'll get minus 2 plus root 3 and I'll get minus 2 here. So this is immediately going to give me the solution for C2 because minus 2 cancel out. I get 2 into root 3. So C2 2 into root 3 is minus 4 plus root 3, and then I can solve C2 as minus 4 plus root 3 by 2 root 3 from this equation here. Now I can simplify this. Of course, I see that root 3 by 2 root 3 is simply going to give me half, and the other term is going to become minus 2 by root 3. So that's the value of C2. Now immediately I can take this C2 and plug it into this equation here. C1 plus C2 is 1, and I get C1 is 1 minus C2, which gives me 1 minus half plus 2 by root 3, which gives me half plus 2 by root 3. Now having got C1 and C2, I can plug it back into the solution of the differential equation, the general solution. So here there is C1, here there is C2, and now I get this nice solution which is often known as the response of the system. So this is something we can plot very easily. That is one of the reasons to obtain C1 and C2. So if we plot it, we of course clearly see that it's a summation of two exponential type of functions. So it comes out something like this. You can see certainly the initial condition is satisfied because x0 is 1, and this function goes up and goes down like this. Now this kind of function, x is a function of t, is known as the response. The differential equation we are doing here is very simple, but you can understand that in almost all dynamical systems out there in physics, out there in engineering and so on, and even applied mathematics, so much effort is spent in differential equations because at the end of the day you want to obtain the response of a system. Now this system could be something like an aircraft, it could be a rocket, it could be a car, or it could be any other system. Now let us take the previous differential equation and we'll create a new question by simply replacing the 4 by 1. So that's the big difference here. The initial conditions are kept exactly the same. So let's try to solve this problem. Now I'm going to try to solve the problem using the same approximation or assumption that xt is e to the power st. I'm going to get the first derivative, the second derivative, plug it back into the differential equation here. That's going to give me the characteristic equation s square plus s plus 1 equal to 0. And then I'm going to try to solve it using the quadratic formula, and now I end up with the I factor here. So what happens is that I have a 1 minus 4 term here that gives me a negative 3 inside the square root. So I have to write this as I root 3. Remember, I is root of minus 1. So these are the two roots here, and so now the solution becomes xt is c1 e to the power of this value plus c2 e to the power of this value, where these two values are essentially s1 and s2, the two roots of the characteristic equation. And we see here also now I is involved, so certainly what's going to happen, the solution at the end is probably going to end up with complex numbers, or I should say it should end up with sine and cosine because complex numbers are involved here in the exponential. So let us take this and let us first try to put in the initial condition. So I take the xt, I differentiate it, and I again put x0 and dx by dt is 0. So I get these two equations, c1 plus c2 is 1, and one more equation here equal to 2. Now of course remember e to the power of 0 again is always 1, so that's happening in all these equations. That's simplifying my life. Now I'll just rewrite these in pink to make it cleaner. So C1 plus C2 is 1 is the first equation, and the second equation becomes this if I take the 2 term here and move it to the right hand side. So these are two equations, again two simultaneous equations which I can solve for C1 and C2. So let us do that. Again, what I will do is, to avoid mistakes, I will take this equation and I will multiply it throughout by the coefficient of C1 in the second equation. That's what I've done here. I've multiplied the equation here by minus 1 plus I root 3. Now I can very easily subtract these two equations. The C1 term will cancel out. I'll get minus 1 plus I root 3 plus 1 plus I root 3 here equals minus 1 plus I root 3 minus 4. So this is the equation. Minus 1 and 1 cancel out. So I end up with 2 I root 3 here. Here I end up with minus 5 plus I root 3. I solve this further, and so I'm able to immediately get C2, and from C2 I am able to get C1 because C1 is 1 minus C2. So here of course you see that in the second term here I root 3 would cancel out in both places, so I'll end up with half, and this term would be simply 5i by 2 root 3, because remember 1 by I is actually minus I, so that comes out here. Now having obtained C2 and C1, I can easily write the equation out here. This is actually the response of the system. But I see the presence of I in exponentials would mean that I could probably simplify it and I could express it in terms of sines and cosine. Let's see if that is possible. Now this is another exercise which is very valuable to test the student's skill, not only in terms of algebraic manipulation, meticulousness and diligence, but also in terms of complex numbers. So essentially what we do, we write this x out here again, and here now what I have done is I have taken the e to the power minus t by 2 term out here, which was present in both these exponentials, and then I have written these complex exponentials in terms of cos and sine. So remember there is a formula here, e to the power ix is cos x plus I sine x, which I'm using here. Now once I use here, I get this equation here, and in this equation what I can do is I can take cos root 3 by t, and I can try to add all the coefficients of that. So again you see there is a half here, there is a half here, that's going to give me 1, and of course this and this 5i by 2 root 3 term are going to cancel. So cos ends up with only coefficient of 1. Now in the case of the sine term, what will happen of course is that this half is going to get subtracted from this one. So after some algebraic manipulation, what I am going to last with is simply the term involving root 3 by 2 by t here, and of course 5 by root 3 here. So 5 by root 3 is going to survive because I'm going to have 5 by root 3 present in both these terms, and then there is going to be an I square involved. The I square is going to give me minus 1, and I end up with this as the solution in green. So this is of course the actual solution of the differential equation after the initial conditions have been included. Now I can plot this differential equation and it comes out to be in this form. So you would expect this because this is a combination of exponential and sinusoidal type of function, and again this is the response of this particular system. Now the reason these two questions and these differential equations are very popular in many interview setting is that they are something which are special cases of the general spring mass damper system, where if m is mass, c is damper, and k is spring, then you would get this equation here. So the first case I consider where mck is 141, that was a specific type of system which is essentially known as an overdamped system. And the second case which I considered is 111, where m was 1, c was 1, k was 1. This is also another special type of damped system which is known as the underdamped system, and depending on that the results turned out to be quite different. The first case you got an exponential solution, in the second case you got a sinusoidal solution which was bounded by the exponential function. Now these kind of differential equations are very important. You can ask them not only to students in the mechanical type of fields or in physics, but also to any particular student of engineering and science, because these kind of equations are quite ubiquitous and they keep showing up every now and then. Now I'm going to give some links on this video at the end screen and even in the description box, which are going to lead you to the particular equation I have mentioned here in terms of MCK, and you can study the differential equations there, because these kind of spring mass damper systems are extremely important in many physics and engineering problems. So I hope that will help you to continue your research and education journey, and I will see you in my next math video sometime soon.